Just 2 days ago, an enormous upper component of an orbital space rocket, measuring roughly the same physical scale as a standard passenger school bus, violently impacted the surface of the moon at an extraordinary speed of 5,400 miles per hour. Absolutely nobody intervened to halt its velocity, and in truth, no engineering team possessed the technical capability to stop it. If you are curious to discover what genuinely transpired during this dramatic celestial event, make sure to stay tuned right here because this narrative becomes increasingly fascinating with every passing minute that unfolds in real time. Please take a moment to drop a comment in the section down below. Simply write the word moon if this extraordinary occurrence blew your mind. Let us jump right into the fascinating details now. So, to understand this event properly, we must travel back in time to January 15th in the year 2025. On that afternoon, the private aerospace corporation, SpaceX, launched a Falcon 9 rocket straight from the Kennedy Space Center, located in Cape Canaveral, Florida. This was far from an ordinary spaceflight mission. This launch vehicle carried 2 separate robotic lunar landing craft into outer space simultaneously on the exact same flight. One spacecraft was designated as Blue Ghost, constructed by an American commercial enterprise called Firefly Aerospace. The second payload was a Japanese robotic lunar lander named Hakuto-R, built by a commercial firm named Ispace. Here we had 2 completely independent spacecraft, representing 2 different nations, riding into space atop a single rocket booster. That is precisely the kind of complex mission that SpaceX performs on a regular basis nowadays. It sounds almost ordinary when described out loud, but what occurred after that initial launch was anything but ordinary. Both landers detached cleanly from the rocket upper stage and set off on their separate journeys toward the moon. Blue Ghost made its way successfully to the lunar ground, where it carried out 14 days of valuable research operations exactly as planned by its design team, achieving a complete mission victory. While the American Blue Ghost lander achieved complete operational success on the surface, the Japanese Hakuto-R mission unfortunately ran into complications during its automated descent and failed to achieve a gentle touchdown on the lunar soil. That result was recorded as a significant disappointment and a total loss for their team. However, right here is where our overarching story takes an extraordinary turn. Once the rocket upper stage completed its primary task of accelerating both payload spacecraft toward the moon, it ran completely out of remaining fuel reserves. It was totally spent, completely empty, and fundamentally exhausted. Consequently, it transformed into what scientists and space trackers categorize as orbital space debris. Essentially, it was a giant hollow metal tube weighing approximately 8,800 pounds, or about 4,000 kilograms, stretching roughly 39 feet in overall length and measuring about 13 feet across its diameter. That is by no means a small piece of hardware. It represents the approximate physical dimensions of an entire school bus floating helplessly through the void of space with no human operator controlling its movement, no crew on board capable of steering it, and no propulsion mechanism left to return it safely back to Earth. Typically, most Falcon 9 upper stages remain in lower orbits relatively close to Earth. Once their missions wrap up, Earth's atmospheric gravity pulls them back downward into the atmosphere where friction completely burns them up cleanly until nothing remains. However, this specific upper stage was sent much further out into space, changing its ultimate fate entirely and leading to an unexpected lunar trajectory. Because this specific upper stage ended up traveling much further out into space than what normally occurs during standard operations, it spent the vast majority of its time navigating at a location relatively close to the gravitational region of the moon. That single circumstance altered the entire situation completely. Far away from Earth, entirely different natural forces begin exerting influence over floating hardware. There is the massive gravitational pull from the Sun, the remaining pull from Earth, and the nearby gravitational influence of the Moon itself. In addition to those gravitational factors, there is another subtle, natural phenomenon that you might never have considered before, which is the physical pressure exerted by solar light. Photons streaming from the sun actually exert a small physical force against solid objects, a phenomenon known as solar radiation pressure. Although this force is extremely gentle and practically imperceptible on a moment-to-moment basis, over a duration of 18 continuous months, these combined cosmic forces quietly, slowly, and invisibly pushed that abandoned rocket stage into an entirely new trajectory. That new path had a definitive collision point waiting at the end. An independent astronomical observer named Bill Gray was the person who ultimately uncovered this impending collision. Bill Gray is not a mainstream public figure, nor does he appear on network television every single week. Yet he is the exact individual who spends his time tracking deep space objects that larger tracking networks typically ignore. He has been conducting this specialized work for approximately 30 years, creating custom software tools that distinguish between natural asteroids and man-made space junk, floating in similar trajectories. When automated sky surveys detect unidentified moving objects, they often call Bill Gray to identify what they are looking at. Back in September of 2025, Bill Gray first observed that this Falcon 9 upper stage was following a trajectory that appeared distinctly concerning. He immediately began calculating the mathematical parameters of its flight path. He double-checked the trajectory over and over again throughout the following weeks, and slowly the complete picture became undeniable. This piece of discarded rocket hardware was heading directly for a collision with the Moon. It was not going to miss its target. Because it had no functioning engine, no remaining fuel, and no way to adjust its flight path, its destination was completely locked in place. Surprisingly, Bill Gray was not panicked or alarmed in the way one might expect. As he later explained to journalists, he had been keeping watch for an event of this exact nature for roughly 20 years, ever since large pieces of orbital debris began accumulating in high orbits that could theoretically cross paths with the Moon. His primary surprise was simply that accidental lunar impacts had not occurred more frequently over the decades. In all of human spaceflight history, only 2 artificial objects had ever been confirmed to accidentally hit the Moon, with the first documented occurrence happening back in 2022. Now, this new event was about to become the second confirmed case. As the months went on, predictions regarding the exact moment of impact grew increasingly precise. The finalized calculation pinpointed the impact time at 6:35 in the morning Universal Time on August 5th in the year 2026. In the United States, that translated to 1:35 in the morning Central Daylight Time. The predicted collision site was pinpointed near a prominent lunar feature called the Einstein crater, located close to the western edge of the Moon as viewed from Earth. Scientists at NASA and various independent astronomical observatories across the globe immediately began preparing for the event. This was not treated as an impending catastrophe to be avoided, but rather as a rare and invaluable scientific opportunity. Having an artificial object of precisely known physical dimensions, structural composition, and weight strike the Moon at an exact predicted time and location is an event that almost never happens in planetary science. When natural meteorites or asteroids strike the Moon, they arrive with zero advance warning, leaving researchers with no preparation time whatsoever. However, this upcoming impact was marked on scientific calendars months in advance, allowing astronomers to point their finest observational instruments directly at the target coordinates and wait. On July 17th, in 2026, a research team published a scientific paper specifically detailing how best to observe the collision event. They calculated the optimal viewing angles, timing windows, and determined which astronomical observatories would have the highest probability of detecting either the initial impact flash or the dust plume that would follow. Roughly 10 days later, on July 27th, another research team from the University of Texas at Austin published their own findings based on detailed computer models simulating the impact. They predicted that the central plume of dust would rise between 45 and 60 meters above the lunar surface, while the surrounding dust cloud would expand outward approximately 113 miles in every direction. Furthermore, the simulation models indicated that this dust plume would appear significantly brighter than the dark lunar background for the first few minutes after the impact, making it potentially observable through ground telescopes equipped with high-speed video recording equipment. The lead researcher of that study, William Joe, specifically reminded observers that the most valuable scientific data would not be found in the brief 1-second flash of the initial impact itself. He explained that many observers might stop recording right after capturing that initial flash, but the real scientific insights lay within the expanding plume of material ejected into space. He urged observers to keep their equipment recording long after the initial collision took place. Now let us examine what actually occurred on August 5th in 2026. At 6:35 in the morning Universal Time, the rocket stage struck the lunar surface. The European Southern Observatory's Very Large Telescope, located in the Atacama Desert in Chile, was positioned precisely toward the target zone and ready for action. Astronomers across North and South America similarly had their observational equipment pointed directly at the impact site. Then, the collision occurred. The 4,000-kilogram hollow metallic structure slammed into the lunar surface at a speed of 8,700 kilometers per hour, which equals roughly 5.5 kilometers per second. Because the Moon possesses no atmosphere, there was no air friction to slow down the falling stage before it struck. The total kinetic energy of the impact was roughly equivalent to 3 tons of explosive energy detonating on the surface. Within minutes of the impact, instruments at the European Southern Observatory confirmed chemical signatures detected inside the ejected plume of material blasted off the surface. They identified the distinct signatures of 2 chemical elements, sodium and lithium. Scientists believe the sodium originated from the lunar soil itself, as the moon's regolith contains natural sodium compounds that get released violently during high-speed impacts. The lithium signal, however, was fundamentally different. Lithium is a critical component used in batteries built into rocket hardware. Researchers concluded that the detected lithium came directly from the rocket's own battery systems, which smashed into the surface and vaporized into gas, creating a chemical fingerprint from both the moon and human hardware mixed together in a plume that drifted through space for 5 to 10 minutes. One day after the impact, on August 6th, the Korean Aerospace Administration released photographs captured by South Korea's lunar orbiter called Danuri. The spacecraft had been repositioned to monitor the collision site, conducting 8 separate imaging sessions. One image was taken 30 minutes prior to impact, while 7 additional images were taken afterward. When comparing the before and after photographs, a dark streak was clearly visible in the later images that was not present before, representing a brand new mark on the lunar landscape. While the new crater has not been measured with absolute precision yet, scientists expect it to be between 20 and 30 meters wide, or roughly 65 to 100 feet across. This is notably smaller than a crater created by a solid asteroid of identical mass because a hollow rocket body disperses its kinetic energy differently upon impact. The unique shape and structural characteristics of the resulting crater represent crucial data points that planetary scientists are studying carefully to better understand how hollow, human-made objects interact with planetary surfaces compared to solid natural meteorites. NASA's Lunar Reconnaissance Orbiter, which has been mapping the moon for years with a proven track record of photographing impact sites, has also been tasked with surveying the new crater location. Scientists expect to eventually obtain much higher resolution imagery of the crater, similar to the results obtained following the 2022 impact event. Looking back at that 2022 collision provides a helpful comparison. In March of 2022, Bill Gray tracked another piece of discarded space hardware on a path toward helpful comparison. In March of 2022, Bill Gray tracked another piece of discarded space hardware on a path toward the moon. There was initial uncertainty regarding which rocket it came from, with some thinking it was an old SpaceX Falcon 9 booster, while others later identified it as part of a Chinese Long March 3C rocket launched in 2014. Regardless of its origin, that object struck the moon on March 4th in 2022. When NASA's Lunar Reconnaissance Orbiter photographed the crash site, the pictures revealed something completely unexpected. Not a single crater, but 2 distinct overlapping craters sitting side by side, each measuring roughly 100 feet across. Scientists had never observed a double crater result from a single natural meteorite impact. The accepted theory is that the hollow rocket structure had concentrated mass at both ends, causing energy to release at 2 distinct points almost simultaneously. That type of surprising, complex data can only be gathered from real-world impacts. With the August 5th, 2026 impact, researchers had significantly more advanced preparation time, superior observational instruments, and comprehensive before and after imagery. What scientists learned from this crash provides immense practical value for future space exploration endeavors. NASA, SpaceX, and other international space agencies are actively working to send humans back to the moon. NASA's Artemis program has already announced the astronaut crew for Artemis 3, scheduled for 2027, which aims to land humans on the lunar South Pole for the first time in history. SpaceX plays a critical role in that plan as its Starship vehicle is designed to land those astronauts on the lunar surface. In October of 2025, SpaceX successfully launched and landed its 11th Starship test flight, marking a major milestone toward carrying crew to the moon. However, before human missions can proceed safely, scientists must understand the lunar environment thoroughly, including how dust behaves during high-velocity impacts and how cratering material spreads across the surface. When astronauts land and construct permanent habitats on the moon, high-speed impact debris becomes a critical safety concern. A surface astronaut or facility cannot afford to be struck by high-speed ejecta material. William Joe from the University of Texas emphasized that future lunar operations depend heavily on accurate physical models for impact plumes and ejecta dynamics. This rocket impact provided real-world data to calibrate those mathematical models against, creating scientific knowledge that did not exist previously. Additionally, there is a broader regulatory dimension to this story that cannot be overlooked. SpaceX director Juliana Scheiman noted shortly before the impact that the trajectory leading to the crash was unintentional but ultimately unpreventable due to depleted fuel reserves. The vehicle simply ran out of propellant, and was carried along by natural gravitational forces. Astronomer Bill Gray remarked that while this specific crash posed no immediate danger, it highlights a broader issue regarding how discarded space hardware is disposed of in deep space. He warned that space is becoming increasingly crowded. Right now, hundreds of thousands of pieces of orbital debris surround Earth. While objects in low Earth orbit face strict guidelines requiring rapid re-entry into Earth's atmosphere, high-altitude hardware faces far fewer rules. As launch frequencies increase rapidly around the world, space debris will continue to multiply. The fact that only 2 accidental rocket impacts on the Moon have occurred in over 65 years of spaceflight is remarkable. But as lunar missions increase, such events will become more common. This crash serves as an important wake-up call for the international community. The rocket stage that impacted the Moon on August 5th in 2026 created a permanent new crater near the Einstein crater that will remain undisturbed for billions of years, as the Moon has no wind, weather, or atmospheric erosion. Scientists continue analyzing the images from Danuri and data from the Very Large Telescope to refine the computer models that will protect future lunar astronauts. Real science is often unpredictable, but unexpected events can provide the most valuable insights of all. If you enjoyed this video, please subscribe, share it with friends, and leave a comment below sharing your thoughts on how we should manage space debris. Looking ahead toward the future of space exploration, managing orbital debris is rapidly becoming one of the most critical challenges facing the global space industry. As commercial space companies and national space agencies scale up their launch schedules to support ambitious lunar programs, the sheer volume of hardware entering Earth orbit and deep space trajectories will increase exponentially. Without robust international agreements, standardized disposal protocols, and advanced tracking infrastructure, discarded rocket stages and inactive satellites could pose ongoing hazards to active space missions, scientific satellites, and future crewed outposts on the Moon. By carefully analyzing unexpected collision events like this one, planetary scientists and orbital dynamicists gain crucial real-world data to refine their mathematical models, improve impact ejecta predictions, and design safer habitats and landing sites for the next generation of space explorers. The valuable insights gathered from this accidental lunar impact demonstrate that even unintentional space events can provide significant scientific breakthroughs, helping humanity navigate the complexities of deep space exploration responsibly as we expand our presence across the solar system. As human civilization prepares to establish permanent research bases and industrial operations beyond Earth, establishing sustainable space practices will be essential to ensure that future generations can explore the cosmos safely and effectively without leaving a trail of hazardous debris behind. Furthermore, international space agencies must collaborate closely with commercial operators to develop innovative debris mitigation technologies, such as active removal missions and autonomous deorbit systems. Protecting the cislunar environment and Earth orbit is vital for ensuring long-term scientific progress, economic growth, and the safe, continued expansion of humanity into deep space. Every piece of data collected from real-world impacts contributes directly to building a safer and more sustainable framework for future cosmic voyages. By maintaining vigilance over deep space tracking and establishing clear international regulations, spacefaring nations can ensure that humanity's ongoing journey into the cosmos remains both inspiring and secure for all future generations who dare to look toward the stars. Together, we can preserve the beauty and safety of outer space while continuing our noble quest to explore the unknown reaches of our magnificent universe, unlocking new frontiers for all of humankind as we venture forward into the brilliant tomorrow.